Welcome to The Explainer. You know, we're surrounded by industrial pipes, but have you ever thought about the hidden engineering battle happening inside them? We're talking about a fight against chaos itself, a fight that breaks out whenever you try to move gas and liquid together.
So let's start with a question. What on earth could make a giant steel pipe, something built to handle insane amounts of pressure, literally shake itself apart? You might think it's some outside force, right? But the answer, and this is wild, is usually something happening inside the pipe, a chaotic internal battle between gas and liquid.
So to get to the bottom of this, we're going to put on our engineering detective hats. We'll start with the two-phase problem itself. Then we'll look at how engineers actually map out this chaos to predict what it's going to do. We'll uncover their secret weapon, a kind of universal speed limit, and see why an expert's judgment is so crucial. And then, just for fun, we'll throw a curveball into the mix and see what happens when you add some grit.
Okay, first up in our investigation, let's meet the main villain of this whole story, a really destructive phenomenon called slug flow.
You know, in a lot of industries, you have to move a mix of gas and liquid through the same pipe. And you'd think, okay, it'll just mix together, right? Kind of like cream in your coffee. But nope, the reality is way more chaotic. If you don't get the design just right, that mixture can do some seriously wild and unpredictable things.
So what is slug flow? Well, picture this. Instead of the liquid flowing smoothly, it starts to clump together into these huge, dense plugs. Now imagine the gas behind it building up pressure, and then acting like a cannon, firing these liquid slugs down the pipe like bullets. That right there is slug flow.
And the damage these things can do, it's no joke. We're talking about liquid slugs hitting with the force of a battering ram. The vibrations are so violent they can literally shake heavy equipment to pieces. Just one of these slugs hitting a pipe elbow can cause a massive failure. And if they manage to get all the way to the end of the line, they can totally flood and overwhelm the systems that are supposed to separate the gas and liquid. It is a total menace.
So how in the world do you fight something like that? A force you can't even see? Well, engineers don't guess. They actually use these special charts. Think of them like a weather map, but for what's happening inside the pipe. It lets them predict and even control the fluid's behavior.
See, here's the thing. This chaos isn't actually random. It follows predictable patterns, what engineers call flow regimes. And these patterns all depend on how fast the gas and liquid are moving. That's the secret. By carefully choosing the pipe size and the flow rates, engineers can basically pick which pattern they want to see inside the pipe.
And here are the main choices they have. They use these special maps, things like Baker or Mandan maps, to predict exactly which regime will show up. The goal is always to stay in the safe zones. You've got stratified flow. That's nice and calm, liquid on the bottom, gas on top. Or annular flow, which is fast but stable. What they absolutely have to avoid is that danger zone, the conditions that create our villain, slug flow.
Okay, so let's say you've done it. You've designed the perfect pipe and you've completely avoided slugs. You'd think you're in the clear, right? Wrong. There's another threat lurking. A much sneakier, slower, and silent killer. Erosion.
And this is where things get really tricky. It's a balancing act. You need the fluid to move fast enough to prevent other issues, like stuff settling out. But if you go too fast, that mixture of gas and liquid starts acting like liquid sandpaper. It just slowly wears away the inside of the pipe, especially at the bends. It's that slow, silent threat that can cause a major failure years later.
So to deal with this problem, engineers have a go-to guide. It's a really important industry standard called API RP14E. And inside this guide is the key, a formula that lets them calculate a kind of universal speed limit to keep that erosion in check.
And here it is. It's called the erosional velocity equation. It looks pretty simple, right? It basically sets a maximum speed limit, V, based on the density of the mixture. But the real magic, the secret sauce, is that little c you see there. That's an empirical constant, and it's the key to the whole thing.
Now here's where it gets interesting. That C value, it's not some universal number you just pull out of a textbook. This is where engineering becomes less of a pure science and more of an art. It all comes down to experience and judgment.
Just look at this table. The right C value depends entirely on the situation. For a standard carbon steel pipe that's always in use, you'd use a C of 100. But hey, what if you use a tougher, corrosion-resistant alloy? Boom, you can use a C of 200 or even higher. And a higher C value means a higher speed limit is allowed, which might mean you can use a smaller, less expensive pipe. It all connects.
So this just goes to show, engineering isn't just about plugging numbers into an equation. An engineer has to use their experience to look at the whole picture, the materials, the risks, how the system is used to pick the right C value. It's a perfect mix of hard science and professional gut feeling.
All right, so we've got slugs and erosion under control. But what happens if we throw another wild card into the mix? What if it's not just gas and liquid? What if there's also sand or other gritty solids in there?
Well, as soon as sand shows up, everything changes. The old rules kind of go out the window. Because sand is so abrasive, speeds that were totally fine before are now unbelievably destructive. That liquid sandpaper effect we talked about? Yeah, now it's turned up to 11.
The risk is so extreme that engineers often just toss out the calculated speed limit. Instead, they'll fall back on a super conservative, really low velocity. We're talking sometimes less than 5 meters per second. They do this just to make absolutely sure the pipe doesn't get sandblasted from the inside out. But this problem also leads to one of the most clever solutions in piping. See, the bends are always the weak spot. So instead of a normal elbow, engineers use something called a target tee or a blind tee. It's basically a T-fitting with one end capped off. What happens is the sand from the flow actually collects and packs into that dead end. It creates its own protective cushion that absorbs the impact from the rest of the sand. How cool is that? The system literally builds its own armor.
So when you boil it all down, designing these pipes is this incredible balancing act. You've got these two competing threats. If you go too slow, you get slammed by the violent, immediate danger of slug flow. But if you go too fast, you get eaten away by the slow, silent killer of erosion. Finding that perfect sweet spot in between, well, that's the real art of pipeline design.
And it really makes you think, doesn't it? How many other invisible engineering battles like this are being fought and won every single day, just to keep our world running safely? All of this is happening in the pipes, the wires, the structures we take for granted, totally hidden from view.